Thank you, Hassan, and also thank you to the rest of the iOptics organizing committee for giving me the opportunity to share some of the results that my group has had in microring resonators over the past, wow, eight years. So I've been at Illinois now. This is my 9th year, and very early in our development as a group, we got interested in the theory and application of reflective microring resonators. And so we'll talk today about how we engineer the mode coupling between the different modes in the microring so that we can have applications in sensing and in lasing. So brief outline, I'm going to talk about some motivation. There's the traditional microring resonator that many of you are familiar with. Basically, light couples in from a waveguide into a microring resonator, and based on constructive interference, the field intensity builds up inside the ring. So our group started looking at reflective microring resonators, where we put a grating inside the ring so that we can generate a reflection spectrum. I'll talk about some of the simulation and design tools, basically our methods of using COMSOL to simulate two-dimensional cross-sections of the mode profile using finite element method. I'll talk about the work that we did to develop a cylindrical coupled mode theory so that we can understand how the different modes of the microring couple to each other and how we can engineer the spectra by doing the selective coupling. I'll talk about the results that we have for passive microring resonators, how we design and fabricated structures in silicon nitride using silicon dioxide cladding, the measurement of these devices so that we can calculate the spectra of the transmitted and also the reflected properties of the device. And I'll show some experimental results where we demonstrated single wavelength reflectors based on our microring design. Next, I'll go into some applications. So the first part of the talk will be mostly about the theory of these devices and give some basic fabrication results. The second part of the talk will go into the applications. So we want to be able to use these devices as these reflective microring mirrors as laser mirrors. So replacing the linear Bragg reflector with this compact microring-based reflector, and we show experimental results of how we did monolithic active and passive integration of a device on a gallium arsenide substrate. I'll then get into our work in single wavelength integrated microring lasers. It's nice to have good acronyms, so we call this device the SWIRL, single wavelength integrated ring laser. I'll talk about how we can engineer the loss of the different modes based on mode coupling, and then show some fabrication results and experimental results about how we can choose the specific resonance, the specific azimuthal order of the resonance for lasing. Finally, I'll go into the application in sensing. So our group is interested in making plasmonic-based, whispering gallery mode-based microring sensors. So this hybrid sensor allows us to detect small biomolecules as it binds to the surface. So the structure consists of this silicon microsphere surrounded by these gold nanoparticles, which we call epitopes. And based on the design of the dimensions of the epitopes relative to the design of the whispering gallery mode, we can engineer coupling between the isolated microring resonator formed by the whispering gallery mode and the plasmonic chain ring resonator formed by these epitopes. And we'll show that based on the device dimensions, we essentially get something like a mode anti-crossing or a band anti-crossing, where we generate the symmetric and anti-symmetric modes. And in this very small variation in the radius, we can get significant changes in the resonance shift due to binding events. Okay, so let's talk about the motivation. So why do we want to study reflective microring resonators? So when you look at a semiconductor laser, typically the end facets are made by linear Bragg reflectors, so alternating high and low refractive index materials, and you make these quarter wavelength long for each section. And this is a well-known reflection spectrum profile which has a maximum in the reflection when the wavelength is exactly such that the thickness is lambda over 4. For each layer. So you can design these high reflective mirrors. Some of the disadvantages of the linear DBR is that it's very long. In order to get high reflectivity and narrow line width, you have to make it longer. So the width in frequency is inversely proportional to the length of the DBR. So if you want to improve the narrowness of this reflection spectrum by a factor of 10, you need it to be 10 times as long. There's also an issue when you start making these gratings to the millimeter to centimeter size, in that you get fabrication non-uniformities. So across the wafer, the pitch that you're able to achieve, the refractive index, the device dimensions, when you fabricate these devices, it becomes less uniform as it spreads out. There's also the issue of these side lobes. So the side lobes are actually additional modes that can laze in your spectrum. They add noise in the overall laser performance. And so although you get the main output power at the peak of the reflection spectrum, you also generate light at these other unwanted wavelengths, which produces laser noise. So our group had a very simple idea. Our idea was just take the linear DBR and roll it into itself and make a ring DBR. And we didn't really fully understand all the great benefits that you can have just by doing this. Our main motivation was we wanted to make a smaller device. So after we started simulating these structures, we found some really nice properties. So the main goal was we wanted to make it smaller. But in addition to this, because it's smaller, it's less sensitive to wafer scale variations. So I'm only patterning a grating over a 60 or 70 micron diameter ring instead of a few millimeters to centimeters long. And I can achieve the same amount of reflection power from my very compact structure that I could from this very long device. So if I want to tune the structure, if I do something like temperature tuning, in the first case I have to temperature tune the entire length of the DBR, whereas in this case I only have to temperature tune a very small microring resonator. So there's less power required for tuning. Probably the biggest benefit of this structure is that there are no side lobes. So these side lobes exist because of the fact that the linear grating has a finite length. And so this finite length introduces zeros into the summation that you would get from adding up the reflectivities. Because this ring is periodic, when you add up the reflections from multiple passes around the ring, it becomes an infinite sum, and this infinite sum does not have zeros. So as a result, there are no side lobes in the reflection profile, and you'll get a much cleaner laser output if you use this as a reflective mirror. So let's look at how we discuss these things. So we have light in a waveguide that couples to a ring. We form the ring just by bending the waveguide into a ring shape. We can easily fabricate one-dimensional or two-dimensional arrays of these ring resonators on chip through standard e-beam lithography. A single microring resonator will have equally spaced resonant modes. At each one of these wavelengths that's resonant, essentially you have an integer multiple of wavelengths fitting inside the circumference of the ring. So when this has a constructive interference such that I have an integer multiple, the power in the ring will build up, and all the power gets lost in the ring instead of being transmitted. So when I'm off resonance, the light goes into the ring, and then it destructively interferes, and then the light couples back out. When I'm on resonance, the light couples into the ring, and it keeps circulating until it builds up in strength, and eventually it's absorbed inside the ring. So at a single resonance, there's actually two degenerate modes. The two degenerate modes are the counterpropagating modes. So there's one that's going clockwise, one that's going counterclockwise, and these have the exact same resonance frequency. So the key that we're going to do with our engineered mode coupling is we're going to couple the clockwise and the counterclockwise propagating modes to be able to form standing wave modes. So the standing wave modes are going to allow us to have high reflection in our device. So we studied the reflective microring resonators using S parameters. We did a simple calculation in MATLAB. We model our system as we have power coming in, and there's a certain amount of electric field coming in. We have a certain amount of electric field circulating in the ring. There's a reflective element, which you can write in terms of a scattering matrix with reflection and transmission coefficients. And what you can calculate is, as a function of the wavelength normalized by the free spectral range of the device, what is the overall reflection of this structure as a function of the reflection that you put, the reflection coefficient of the element that you put inside this ring. So we get a profile that looks like this. So this is a plot. So for a fixed amount of coupling into the ring, for a fixed amount of loss, we generate one of these plots. And this plot allows us to design the type of reflective element that we put in the ring so that we get an overall reflection spectrum that's useful for a device. So as an example, if I wanted to design a structure that reflects exactly at this one wavelength and doesn't reflect at any of the other resonances, what I need to do is I need to construct a wavelength-dependent reflector inside the ring that goes through the maximum in this curve here and goes through nulls at all these other resonances. If I can construct such a device, then the overall structure will have one reflection peak in it, and all the other resonances will be non-reflective. So I want to construct a device that has this particular reflection profile. It's reflective. In this case, it's like 5% reflection at this one wavelength, and then it has no reflection at these other wavelengths. And so if I can construct such a device, then the combined response of the overall ring plus reflector will have high reflectivity at my design wavelength, and then I'll have the suppressed reflectivity at the other resonances. So at these other resonances, the field wants to build up and become stronger because it's a resonant condition, but at the same time, this element is becoming non-reflective. So as a result, the overall reflection will be very small. So how do I construct something that has this profile? It turns out that if I put exactly half the grating filled with this linear DBR, then I get these reflection nodes. So in the linear DBR, it's a bad thing, but when I combine it into the ring, I get the exact spectrum that I want. And it turns out that if this is exactly half, then I get the nulls at exactly the resonance wavelength of the other resonances. So this combined structure gives us high reflectivity at the design wavelength and no reflection, or in this case, minus 40 dB in terms of reflection at the other resonances. So if I zoom in, I can see I have a nice reflection at that one wavelength. The transmission goes down. And then at the other resonances, the reflection is 0. So this will form the basis of a single wavelength mirror. So if I want to make a laser and I want it to be operating at a single wavelength, if I put this device as the output or as the high reflectivity mirror in my laser cavity, then this structure will reflect and give me a lasing condition at this one resonant wavelength. And all the other wavelengths will be not able to lase because the loss going from the mirror is going to be very high because it has very low reflectivity overall. So now let's shift into the simulation and design tools that we use. So our group does quite a bit of modeling depending on what program we use. We combine COMSOL modeling. We also do modeling in MATLAB. We're collaborating with Professor Jin's group to do computational FEM. So we have all these different simulation and design tools. So I'll talk about our simplified versions of the tools. So in order to design a general microring reflector, we want fast and accurate simulations. The challenge with simulating a microring resonator is that since the dimensions are very large compared to the wavelength, and since the dimensions it's a three-dimensional structure, you need a lot of memory and you need a lot of computational power to be able to accurately simulate it with a brute force method. So one of the quickest things that you can do is notice that the modes have an azimuthal dependence of the form e to the j nu phi. So taking off this azimuthal dependence allows you to reduce the problem from a three-dimensional problem into a two-dimensional problem. And so typically we simulate the mode profile in this two-dimensional constant phi plane where we plot as a function of radius and a function of z the mode profile. So this tiny blocks here is the core surrounded by some cladding material, and then based on the way that we fabricate it, we actually have some more unwanted material at the side. So in order to study the effect of the gratings that we're putting on our structure, what we wanted to do is develop a cylindrical coordinate coupled mode theory. So coupled mode theory is well known in Cartesian coordinates. It's very easy to write down. Well, I should say very easy in the sense that you have to look up a bunch of papers and then it becomes very easy to write down. But what we wanted to do was we wanted to study the coupling between the clockwise and the counterclockwise amplitudes of the mode. So what we developed, well, we write out Maxwell's equations, we do a whole bunch of algebra, we simplify it using these approximations, and we get a differential equation that talks about the coupling of the forward and the backward propagating modes. This coupling matrix, what you have to do is you have to calculate the electric and magnetic fields and then compute various integrals of the electric and magnetic field, tangential and parallel components over cross-sectional areas. So in this paper, you can figure out what these integrals you have to compute is. But basically, all you need to do is simulate the two-dimensional cross-sectional profile for electric and magnetic fields, and then calculate a bunch of integrals based on that. And this allows you to figure out how do the forward and the backward waves couple to each other. So we verified this with FEM simulations. So the FEM simulation that we did was a two-dimensional simulation. So the method that we developed is good to run in 3D. However, the commercial software we're validating it against doesn't have enough memory to simulate in 3D. So we did a simulation in 2D where this is the same structure in the out-of-plane direction. So a two-dimensional simulation of this reflective microring. And you can see that we have these nice standing wave generated from sending light in and then having it highly reflected. And we get very good agreement between the finite element method in COMSOL and our cylindrical coupled mode theory. Next, we wanted to look at some nonlinear effects. So we wanted to study the self-heating dynamics that occur in microring resonators. So basically, as you send power into this microring, the amplitude builds up in strength because we have constructive interference. And this increase in power that's circulating inside the ring, there's this tiny bit of absorption that causes heating of the ring, which changes the refractive index, which therefore shifts the resonances. So we wanted to study the time domain evolution of the optical properties of the ring. So we developed time domain coupled mode theory plus a lump thermal circuit model. So we have these equations, which are just the standard coupled mode theory in the time domain. Plus there's this thermal model where we consider that the core is the source of heat. So when the light is propagating in the core of the waveguide, if there's absorption, there's a certain amount of heat generated given by alpha Q. There's a certain amount of heat that's generated in the cladding, which is oxide, given by 1 minus alpha Q. And then there's thermal resistance between the core and the cladding, between the cladding and the substrate. And these are also heat storage materials. So there's a thermal capacitance from the core to the substrate and from the cladding to the substrate. And we get an equivalent circuit model that looks like this. So there are heat sources and there are capacitances and resistances in the structure, and you can calculate the temperature at different parts of the device. Based on this model, you can then predict what happens if I sit at a specific wavelength relative to the resonance and I put in a pulse of optical energy. So this pulse of optical energy, essentially in this graph, we have this turning off, and so there's a certain time constant in which this decays. So we get a certain time response that we measured experimentally and validated with our simulation. Okay, so now let's talk about the structures that we fabricate and how we test them. So in our general setup, we have a tunable laser, isolator, polarization controller. So we can control the polarization whether we launch TE or TM polarized light into our device under test. This polarizer ensures that the polarization is aligned to the direction that we want. We have a reference arm that measures the power that we're putting in, a circulator so that we can send the light to the device under test, and the reflected power gets measured by the reflection detector, and then the transmitted power goes to the transmitted detector. And on each of these fibers are lensed tips so that we can focus light from the fiber into this Microring Resonator chip. And I'll explain how we were able to achieve these measurement results of having a single reflection peak. So our structure consists of silicon nitride core on a grown thermal oxide of SiO2 on a silicon substrate. And so we designed this using the simulation methods I previously described. We fabricated these structures with e-beam lithography, so thanks to Edmund and some of the others in the MNTL cleanroom for helping us with the fabrication. So you can see the Microring Resonator, the scale bar is about 15 microns, and we made different types of indentations to form our reflectors. So in this case, we made 50 nanometer indentations in the waveguide width. In this case, we have a waveguide that's here, and then we have a separate grating structure. So the evanescent tail of the mode in this waveguide couples with the grating that's on the separate region. And then we measure the reflection and transmission setup or spectra with our setup. So the design wavelength, so when we did the first run of devices, we didn't have accurate numbers for the refractive index of silicon nitride or for silicon dioxide that we were depositing. So our first design, we wanted to get wavelength being 1550 because that's the center wavelength for the C-band, which is the wavelength that has the minimum loss in optical fiber. But our first set of devices came out at 1500 instead of 1550. And the main source of error was the refractive indices that we assumed. So we assumed that the value of the refractive index of silicon nitride was 2. It turns out that it's 1.98. And that very small change of 1% is enough to shift some portion of the spectrum. There are some other errors in the dimensions and the values of the refractive index of the core of the cladding that also contributed to this shift. So what we did was, okay, so the wavelength that we wanted was incorrect. So how can we accurately measure the wavelength or the refractive indices of our devices? Well, one thing to notice is that the resonance wavelengths depend very critically on whether it's TE or TM polarized light. So you get different effective indices for different modes of propagation, and based on these resonance locations, the difference between TE and TM, and also the geometry, the free spectral range, which is the separation between adjacent resonances, the free spectral range plus the TE and TM dependencies, these determine where these resonances lined up. So we measure for a single microring resonator the positions of these resonances, and from this we can infer the refractive indices of the core and the cladding material. So we get a measurement of 34 resonance wavelengths, we form it into a vector. And then we have to somehow resolve the ambiguity that occurs in microring resonators. So there's no way to tell from the spectrum whether this is the 200th mode or the 201st azimuthal mode. But with a reflective structure, we know that this particular resonance corresponds to the 200th mode. So by using the reflection peak, we're able to resolve the mode ambiguity. And based on that, we can then say, okay, this is the 200th mode, this is the 199, this is 198, 197, and so forth. And we can uniquely identify each mode. So in order to calculate the parameters in our model, what we did was we linearized the relationship between what we measured and what our initial guess is based on the model. We calculated based on the model the sensitivity matrix. The sensitivity matrix tells us how much does the predicted wavelength change when I change a parameter such as the width of the ring or the refractive index of the core or the refractive index of the cladding. So based on our measured values of the wavelength, our initial simulation based on our initial guesses for the parameter, this allows us to solve for how much we have to adjust the parameters so that we get an agreement between our measured data and our predicted simulation. So we want to minimize this, so we minimize the difference of this equaling 0. So we do a singular value decomposition to find the parameters. It turns out that although we have 34 measured parameters, there are only 4. The rank of this matrix S is only 4. So we can only accurately determine 4 parameters in our model. And the key parameters are the refractive indices of the core and of the cladding, the thickness of the core, and also the chromatic dispersion. So the reason that we only have a rank of 4 is that when you look at the spectrum, it's pretty much determined by TE versus TM and also the free spectral range. All these other resonances all agree with, if I give you those 4 quantities like the resonance location of one of the resonances for TE plus the free spectral range for TE, the resonance wavelength for TM plus the free spectral range for TM, those 4 parameters pretty much determine these entire spectra. So the rank of our measured or of our singular matrix S is only 4. So we're able to achieve very accurate results for our model parameters for 4 parameters. So we determine refractive index of the core with a precision of essentially 4 decimal places, the cladding to 3 decimal places, and then the core thickness to, it looks like 1 decimal place, and the dispersion to essentially 100%. It's not very well, it's not very accurate. We also measured these resonances as we changed the temperature. So when you change the temperature, there's a change in the refractive index due to the thermal optic effect. So these resonances we tracked as a function of temperature, and by measuring a best fit slope and also modeling the effect of TE and TM, we're able to extract the thermal optic coefficients of silicon nitride and silicon dioxide. So this is a method that allows us to figure out what's going on in our device geometry and our device parameters from observations of the resonances of the ring. The reason that this method is very accurate is because we can determine the resonant wavelength of the ring to on the order of like 1 picometer in a measurement that has 1550 nanometers. So it's essentially about 6 or 7 digits of precision that we can measure these resonance wavelengths lambda. So then the question is, how precisely can we model the structures? And it turns out that we can extract several digits of precision in our parameters, both for the parameters at room temperature and also their dependency on temperature. So based on these new values, we fixed all the designs. So now that we know the actual refractive indices, we constructed a second generation of devices, and we hit exactly the wavelength that we want. So we were targeting 1549, we got 1549, or we're targeting 1550, we got 1549.6. So within 0.4 nanometers of our target wavelength by having very accurate model parameters. These ripples, these are due to the end effects from the fiber and also from the facet of the chip. So by doing a model-based data interpretation, so basically you have a measurement, you model the entire system, not just the microring, but also the end facets and so forth, you can extract the effective reflection of just the ring itself. And you get this red dotted line. And if you compare this DBR structure that's in a ring to what you get from the linear DBR, you can see two things. One, we've gotten rid of the ripples, so there aren't these ripples in the spectrum, but also the roll-off is much faster, so this device will be better for single-mode operation. So we achieved 93% reflection, 0.4 nanometer full width half max, and the overall structure is 70 times smaller than the conventional DBR structures that you'd find in a semiconductor laser. We got rid of the side lobes, and we also have a faster roll-off. Okay, so now I'm going to move into the applications. So the first application that I'll talk about is how we make a single wave, well, how do we integrate an active laser with a passive microring mirror? So what we want to achieve is a device that has a single wavelength of lasing, and the lasing being determined by the passive section, which has the microring grating mirror. So the advantage of this microring reflector is that it has a very narrow reflection bandwidth. This narrow reflection bandwidth means that the device will laze in a very specific wavelength. And this specific wavelength allows us to use this reflective microring resonator as the mirror for a single mode laser device. So we're trying to make a compact replacement for the linear distributed Bragg reflectors that you'd find in conventional semiconductor diode lasers. There's another advantage of using passive mirrors. So this is, if you look at the theory, Shallow Towns theory, and also study the Henry line width enhancement factor, there is a benefit of having a wavelength-dependent mirror. If you lock your laser to the right side of the resonance peak and you have this wavelength-dependent mirror, you can reduce the line width by this factor FC squared compared to a plain laser. And so if you want to make a laser that's useful for spectroscopy so that you can have precise wavelengths in your measurement, then the line width becomes a limiting factor. And so being able to reduce the line width is a very important goal of making these semiconductor laser diodes. So having a wavelength-dependent mirror, which is what we have from our reflective microring, so we have this nice wavelength-dependent mirror, so there's a very sharp change in the reflection as I vary the wavelength. This will make a nice mirror that locks the wavelength of the laser. So this laser that we constructed, it has amplification section, so there's a gain section, there's this optional phase section, and then you have this passive section where you're not injecting current, and so there's going to be less noise because this mirror is going to serve as a wavelength lock for your laser. So the goal is to achieve a single wavelength out of our device. Now there's another application, which is if you put these two structures, instead of having a single wavelength in the reflection spectrum, if you can generate a comb of reflection peaks, and you can do that by putting a single notch, then you can have two different free spectral range for the mirror reflectivity. And by aligning these up using the Vernier effect, essentially if I have a set of resonances here and I have a different spacing, when I get one of these to align, then that's going to be the wavelength that lasers. And then I just need to make a very small shift in one of the mirrors to line up a different resonance, and that gives me a large tuning. So I can get quasi-continuous tuning over a large wavelength range by using the Vernier effect if I can get the free spectral range to be different for the two different mirrors. So this is one application we're interested in. We haven't fabricated any of these devices. I'll talk about this device because we have that fabricated. So in order to integrate active sections with passive sections, we had to do a bit of work in the device design and fabrication. So we have this material which is grown for us by epitaxial growth, MOCVD growth by a company called EpiWorks in Champaign. So we have the conventional gallium arsenide core surrounding indium gallium arsenide quantum well. And then we have this indium gallium phosphide etch stop layer in these two locations. We have this undoped aluminum gallium arsenide bottom cladding. And then we have N-type and P-type aluminum gallium arsenide to form the separate confinement heterostructure so that we can separately confine electrons and optical fields. And then what we're going to do is, normally this quantum well will be in the very center of the core. We're going to shift it up slightly so that in one section of the device we keep the full length so that this is the active section. In this other section of the device, we're going to etch away all this material, including the quantum well. And so without the quantum well, this section becomes a passive section. So it works as a transparent waveguide that's made of just gallium arsenide. So what we need to do is we need to go from this active section, which has the quantum well and has the mode sitting way up here, to this passive section where the mode is going to sit much lower down in the gallium arsenide core. So we form this adiabatic horizontal taper where we taper the ridge waveguide etch, and we also taper underneath so that we can confine the mode and transition it from being centered in the quantum well region to be centered in the core / bottom cladding. So the mode is going to transition downwards from this active region into the passive region, and then it's going to couple into the reflective microring resonator, which is going to serve as our laser mirror. So we fabricated these structures. This is a picture of it where we have the active section, we have our taper, we go into the passive section, we have our reflective microring resonator, and because we don't want any light reflecting back from an end facet, we split out the power so it just dissipates into the substrate. So our output facet is going to be to this side is just serving as a high reflectivity mirror. From this structure, we achieve single mode operations, so we get lasing at a threshold of about 30 milliamps for a device that's 1100 by, I think this was 1 micron wide. And you can see that lasing exists and that we have single wavelength operation. These other notches, these are from the higher order resonances of the ring, and we've effectively suppressed them compared to the dominant mode that we wanted to achieve. So the second type of device, and I should mention with this structure, what we do is we have these gratings that form a first order grating. So a first order grating, the length of the section is lambda over 4 long, the period is lambda over 2. A first order grating is designed to reflect light in the opposite direction. So if I send light in the forward direction, a first order grating will directly couple to light in the counter-propagating direction. There's also the second order grating, and a second order grating, what it does is it couples light not only to the forward direction, but it also couples light out of the plane of the direction out of the plane. And so you can generate lossy mirrors if you pattern a second order grating. So we have the swirl device, single wavelength integrated ring laser, and the idea is that ordinarily all these modes that have different azimuthal mode numbers and that are degenerate because they're clockwise and counterclockwise propagating modes, they all had degenerate loss, so they're all the same. We increase the loss of all the modes except for one, and that one mode is the one that's going to laze. So we can show that we can get single wavelength operation for a specific azimuthal mode order, and if we change the azimuthal mode order of the grating, we can get a different mode to laze. So the microring cavity laser, we want a small footprint, low threshold for applications like photonically integrated circuits, on-chip optical interconnects, and short-distance optical communication. The microring and microdisc lasers can be good candidates. They're small, but one of the biggest issues with the microring and the microdisc is that they have many modes. So all the different azimuthal mode orders, like m is equal to 200, 201, they all have the same amount of loss. Moreover, at a single resonance, they have two counterpropagating modes that have the same loss. So the question is, can we engineer the mode coupling to select a specific lasing mode? Can we do this by putting a grating on our structure to increase the loss of all the modes except for one? The answer is yes. And so the way that you do this is you form a grating with azimuthal mode order M. And so that puts a perturbation on the cavity of the form sine of m phi. What this does is, if I have the ordinary mode n for the ring and I have the grating with mode m, I scatter into modes n plus m and n minus m. So when you think about what happens when I multiply sine of n phi times sine of m phi, I get the sum and difference frequencies, and so I generate things that radiate into these higher order modes. So if I have a difference of n minus m equals 2, what I'm going to do is I'm going to couple the light from the azimuthal mode n with the grating of order m into a mode n minus m equals 2, and since this has low azimuthal mode order, it's going to radiate in all directions. And so you can see that this corresponds to rotational symmetry 2, so it radiates and so it has higher loss. So the radiation modes of small azimuthal orders have small quality factors. So by putting the second order grating on the structure, I can select a specific lasing mode. I'm going to set m is equal to n, and I'm going to reduce all the quality factors of all the modes except for one mode. So there's one exception, and I keep bringing this up, but the one exception occurs when n is equal to m and the electric field is shifted by exactly 1/4 wavelength relative to the grating. So if I have a cosine m phi dependence on phi and of a sine n phi dependence of the grating, when I multiply these two together, the sine times the cosine gives me the sine of the double angle. I don't get a DC component. I don't get a low frequency component, and the low frequency component is precisely the component that radiates. So this one particular exception gives me something that doesn't radiate, and therefore the quality factor of this mode is not reduced by the presence of the grating. So I can generate something that doesn't radiate. It propagates it's a standing wave inside the cavity, and instead if I have the sine m phi, then sine m phi times sine m phi, I get the sum and the difference, and that radiates. So to confirm this, we did FEM simulations, and we can see that we have this one resonant mode that doesn't radiate. This one radiates like the spherical harmonic Y00. These ones radiate like LM, where L is -1 or +1, and so all the other modes start to radiate. And so as a function of how deep or how strong I make this grating, I can see that this one mode, which is non-radiating, the loss does not change no matter how I change the grating. Whereas these other modes, the losses increase as I increase the strength of the grating. And so if I have a specific indentation size, I can select this mode compared to the other modes. So for the device design, we have a similar structure as before, except it has fewer layers than what we did for active-passive. And one of the key parameters in terms of this design, because the light is circulating radially, is how deep I etch to form my ridge waveguide. If I etch too deep and I etch into the quantum well region, then I create surface defects, which is going to increase the threshold because I have high non-radiative recombination. If I etch too shallow, then the light that's propagating in the ring can radiate radially outwards because there isn't tight enough confinement to guide the mode inside the ring. So there's a function, as a function of to how deep I etch into the core. So the quantum well is 80 nanometers into the core. If I etch very close to that 80 nanometers, then what I get is I get very low bending loss, and I have high quality factor. If I don't etch deep enough, so I'm sitting here, then I have very high bending loss. So 10 inverse centimeters is pretty high for a laser to operate. And so what I want to do is I need to etch somewhere between 40 and 80 nanometers into the core. If I etch too far, I get high threshold because I have non-radiative recombination. If I etch too shallow, I also get high threshold because I have poor optical confinement and I have high bending loss. So We designed and patterned these with e-beam lithography. You can see the grating formed in gallium arsenide. So this is 3,5 material. The passive structures were in silicon nitride. So this is a completely different etch process compared to the passive structures. We put metal on top of it, and we transfer the pattern with ICP-RIE. We then planarize it with BCB so that we can make metal contacts, and we have separate contacts for the bus waveguide and also for the ring section. So the left 450 micron section was pumped so that we can get to transparency. The center part is the part that's lasing. The right part is unpumped so that it's absorbing. So our laser cavity is formed just by this section alone. It's a circulating ring configuration for our laser. The bus waveguide allows light to couple out from the ring into the waveguide, and this is at transparency, so we let light come out the left side. So as a function of the current, we can see that we get an increase in power, and so we have lasing threshold at about 26 milliamps. When we set n is equal to m equals 724, we get this one resonance as the lasing operation. When we change the azimuthal mode order, so that we can see whether it's the grating that determines the lasing, we can see that it shifts exactly 4 orders to the 4th resonance to the right. And so we have precise control over the wavelength that lases in the structure by defining the azimuthal grating. So the key to getting single mode operation, we've made structures that looked identical to this but without the grating. Without the grating, you get resonances, you get all these resonances competing for lasing, and it's a multi-mode structure. But with the grating, we get single wavelength operation. So for the final part of the talk, I'll talk about our work on hybrid whispering gallery mode plasmonic chain ring resonator sensors. The idea, as I mentioned before, we have the silicon microsphere, which is about 30 microns in diameter. Around the perimeter, or the circumference of it, we put these gold epitopes, which are going to serve as plasmonic chain. And the gold epitopes allow tight field confinement in the vicinity. And so we're going to try to detect the presence of a Thyroglobulin cancer marker protein attaching to these gold epitopes. And we see that based on the design of the epitopes, we can couple effectively between the whispering gallery mode resonances and the plasmonic chain ring resonances and get the sharp increase in the creation of symmetric and anti-symmetric modes. And this is a result of mode coupling between the plasmonic chain and the whispering gallery mode resonator. So as I mentioned, we're looking at the TG cancer marker protein, and so we have these gold epitopes, which are basically gold nanoshells surrounding silicon nanospheres, and we place these around the equator of a whispering gallery mode resonator. Don't ask me how we're going to do this experimentally. This is a simulation work. There's a group that we collaborated with at NYU, and they have methods to use optical gradient force to trap particles around the perimeter of these spheres. Whether they can get it exactly the way that we simulate or not is still an open question. But the point is that we're going to trap or place these epitopes at these antinodes of the field. And in order to simulate the structure very efficiently, so this structure is about 30 micron radius, we want to simulate using the symmetry that exists in the problem. So we're going to put perfect electric conductors at the nodes and perfect magnetic conductors at the antinodes and use periodic boundary conditions to essentially solve for the entire structure. So the field is localized near the epitope. If I change the epitope radius slightly, then I can get distinct coupling regions in this hybrid resonator system. As I mentioned, we modeled this in 3D using periodic boundary conditions with PECs at the nodes and PMCs at the antinodes. So this is what the field distribution looks like as I vary the radius. So there's a lot of parameters in this model. So there's like the radius of the microsphere, there's the radius of the epitope, there's the thickness of the gold coating, there's the spacing. Do I put these at every single node or every other node? There's a lot of parameters involved. So we fix the thickness of the epitope at 10 nanometers. We also fix the position of the epitopes at the antinodes so that it has the strongest effect. And we looked at 2 different cases of the radii. So when the radius is small, 30 nanometers, and when the radius is large, there's a very small perturbation in the mode profile due to the epitope. So this is the cross-sectional view in Z and R of this section of the field. And you can see that we have the field polarized in Z, and the epitope has a very small effect on the overall field shape. When I have a radius of 50, I get slight bending in the angles of the vectors near the epitopes, but there isn't a huge change in the overall electric field profile. This, however, is completely different if I tune the radius of the epitope to the resonance of the whispering gallery mode. So when the radius is 40 nanometers, the plasmonic chain ring resonator and the whispering gallery mode resonator, these modes couple to each other. So the hybrid WGM-PCRR, I generate a symmetric mode and an anti-symmetric mode. So compare the previous case where the electric field profile for the microsphere extends very far in Z and is spread out in R, to this case where it's very tightly confined in Z, pretty much at the locations of the epitopes. And so this symmetric mode very tightly confines the field at that location. The anti-symmetric mode, I end up with the fields pointing in the opposite direction at this location. But again, I have a significant enhancement of the field strength at the plasmonic chain epitope location compared to this diagram. So there's a significant increase in the optical confinement at that location. So we wanted to understand this behavior. It turns out that this is very simply explained as the coupling of two separate resonator systems. So one is the whispering gallery mode. The other is the plasmonic chain ring resonator. So if you model the plasmonic chain by itself, you can see that it has certain field localization properties that basically confine the field very tightly near the plasmonic chain. And so when we look at modal dispersion, what we can plot is, as a function of the size of this epitope, what are the resonance wavelengths of the whispering gallery mode and of the plasmonic chain. So the whispering gallery mode microsphere, it doesn't matter what the plasmonic chain is doing, it has the same resonance wavelength. So that's this green curve here. If you look at the plasmonic chain ring resonator by itself, it has a sharp dependence on the radius. And so this is this black curve here. And so initially, we're expecting the coupling between this green mode and this black mode. However, there's a perturbation, and the perturbation is very important. These epitopes from the plasmonic chain ring resonator are not isolated. They're perturbed by the silicon microsphere that's sitting in the center. So if you do a corrected calculation of the plasmonic chain ring resonator in the presence of the silicon microsphere, you get this black dotted line. And then when I look at the mode coupling between the black dotted line and the green line, I generate the symmetric mode, which is in red, and the anti-symmetric mode, which is in blue. And I can understand the existence of these two separate curves as simply mode coupling between the plasmonic chain and the whispering gallery mode. So the localization of the field at this epitopes is stronger when we're in the strong coupling regime where the radius is close to 40. So when I have a TG binding event on one of the epitopes, I'll get a resonance wavelength shift. And this is how I'm going to sense the TG cancer markers. I'm going to look at the resonance of the microring and figure out, or of the microsphere, and figure out has it shifted. So at this value of 40 nanometers, I get a 20 femtometer shift. Now you say to yourself, 20 femtometers seems incredibly difficult to measure experimentally. But it turns out that this marker is so small that there aren't any other good techniques to detect it. It's a few nanometers. It's basically an ellipsoid that's like 10 or 12 nanometers in one dimension and 5 nanometers in the other dimension. And the refractive index is pretty much the same as the refractive index of the fluid that it's in. And so as a result, any other method is not really going to be sensitive to the sub-wavelength type structure. So this method, we get a 20 femtometer shift for the symmetric mode. Unfortunately, when you're looking at a microring-based sensor, what's important is not only how much of a wavelength shift you generate, but how narrow are the resonances that you're measuring. Because the narrowness of the resonance that you're measuring determines the error that you can make in determining the resonance wavelength. So when we start increasing the shell radius, unfortunately, the quality factor of the ring decreases significantly. And so as a result, it becomes difficult to measure the small shift. So there may be an optimal point in here, depending on the instrumentation that you have, whether you're limited in terms of the measurement accuracy of the tunable lasers you have, where you can trade off a larger resonance shift for having a wider resonance, or you can have a smaller resonance shift for having a narrower resonance. So there are a bunch of trade-offs in this design, and so if you look at the case where you place an epitope at every single antinode, we call this the amount of shift you get for one epitope per one wavelength, or one antinode. And so that's the largest case. So you get the biggest resonance shift. Unfortunately, you get the smallest quality factor. If you space them further apart, and so you put one epitope every other antinode, then you get a smaller resonance shift, but you have a higher quality factor. So if you have just a single isolated epitope by itself, this has a high Q microring resonator. So the advantage is that it's easy to measure wavelength shift. The disadvantage is you only have one binding site. So the probability that the TG marker is going to attach to that one specific epitope that you place is very, very small. And so you have to wait a long time to be able to detect this TG biomarker. If instead you have a certain number of coupled epitopes, you have a lower Q, but now you have n times the detection frequency because you have essentially n sensors distributed around your microring. So you wait less time to detect this biomarker. And so if you place them at every single antinode, then you get the most frequent detection, and you can still trade off the coupling by balancing the effects of sensitivity. So if I place them at every single node, or antinode, I mean, I get very high sensitivity, but I have low Q. If I place them every other, I have lower sensitivity, but I have better Q. So I can trade off those two parameters while still reducing the detection time compared to just having a single isolated epitope. So in summary, we presented our work on the development of new types of devices that operate based on selective mode coupling. This mode coupling is sort of an emerging theme that's in a lot of our group's research, basically looking at the existence of many different modes and how to engineer the coupling between these modes to generate the type of devices that you're interested in. We pursued two types of approach. One is to couple the modes for achieving reflection. So first order grating gives us nice reflection. Two, a second order grating modifies the radiation losses and allows us to generate a single wavelength laser. We developed simulation models, the cylindrical coupled mode theory. We designed and fabricated passive devices, and we demonstrated single wavelength operation. This device is also useful for allowing us to measure the refractive index because it allowed us to determine the azimuthal mode order without ambiguity from the symmetry. We also developed a monolithic integration platform. So we have active laser devices, passive microring reflectors, and we show that we can integrate these two things together. We fabricated lasers that have these mirrors and showed single wavelength lasing, single mode lasing. We also proposed and demonstrated engineering the radiation quality factor using a second order grating so that we get one particular mode that lases and the other modes are radiating. We verified this experimentally and showed that you can control which mode lases by controlling the azimuthal mode order of the grating. And then in terms of our sensor, we looked at the distinct coupling regions between the whispering gallery mode resonator and the plasmonic chain ring resonator. And we showed that you can make trade-offs in the sensitivity and the detection time and the measurement limitations of the quality factor. There's very strong field localization and mode splitting that occurs if the size of the plasmonic chain ring resonator epitopes exactly lines up the resonances with the resonances of the whispering gallery mode. And we showed the existence of the symmetric and the anti-symmetric modes at that critical value. Our future outlook, so the reflective microrings with small footprints are going to be very useful for semiconductor lasers. We really want to expand our work in terms of making these low threshold laser devices, especially for applications in sensing and spectroscopy. There are new designs that our group is studying. So one example is to have instead of having these epitopes sitting around the perimeter of a whispering gallery mode structure, instead make plasmonic bow tie antennas on top the surface of our microring resonator. And so we may be able to localize the field very strongly. So this is the gold plasmonic bow tie structure on top of a microring resonator. We may be able to tightly confine the optical mode in this plasmonic region. And then if we have binding events, we'll have very strong shifts in the resonance wavelength of the structure. And so we may be able to enable field localization without a huge penalty in the quality factor. And finally, we're also looking at practical single-mode low-threshold lasers with further optimization of our fabrication processes. There's a lot that goes into fabricating a device, and there's a lot of work in terms of developing processing recipes to achieve high performance, and so we're still working on that. So for acknowledgements, none of this work would be possible without the excellent effort of the graduate students. A lot of this work was led by Amir Arbabi and Youngmo Kang, with contributions from Josephine, Masa, and Hassan. The funding was from National Science Foundation, the Career Award, and also matching funds from the University of Illinois. So thank you for your attention, and I'm open for questions.